Welcome back, everybody. So we have joining with us in this continuation of who could and couldn't make it from abroad to join us. Egozy is joining us from MIT, Massachusetts, the Massachusetts Institute of Technology. He very recently, I suppose he'll present about these things, but he very recently opened up, or is opening up, a music technology program at MIT. Before that, I won't give his entire bio because we're already behind, but I'll say that he worked for Harmonix, which is the company, or worked for, I guess he's one of the founders, if I'm not mistaken, the company behind Guitar Hero, and among other things. And yeah, without any further delay, Egozy, the floor is yours.
Okay, hi everyone. Thank you, Bud. Okay, I'll just get started. I have great to be here. Sorry I can't be there in person, but yeah, I'll talk about some of what's happening here at MIT. Some exciting new things. So hopefully you can see my screen now, and yeah, I'll get started. So a little bit of background. So this is me. I play clarinet. This was when we just moved to America here. I went to MIT in the early 90s. I studied electrical engineering and computer science. I continued playing music all the time, so these were two wonderful things I love to do, but they were kind of separate pursuits until I got to this. This is the Media Lab at MIT, where I was a graduate student. I worked with Todd Mackover, and then really discovered that music and computation and technology can be combined together. From that, we started the company Harmonix, and we made some games. Maybe you've heard of them, like Guitar Hero and Rock Band. And we made a Beatles game, which was this fantastic experience. But then after 20 years at Harmonix, I came back to MIT, where I now teach and conduct research in interactive music. And I just want to give you a little bit of a sense of what music is like at MIT. It's not a place where you might think music is thriving, but it's actually a pretty fantastic program. For example, we have 1,500 students every year taking at least one music class, where MIT has 5,000 undergraduates. There's only 10 music majors per year, so people do not come to MIT major in music, but when they arrive here, they realize that music is amazing, just like I did when I was here. It's like a little conservatory of music here at MIT. We have courses in music theory, composition, history, culture, ethnomusicology, lots of performance of all types, from regular classical music to jazz and all kinds of world music performance. Here you see the Balinese gamelan performing a piece, and of course music technology, which is now becoming much larger. So I'll spend some time kind of basically two things in this talk. One is to just show you where we're going with music technology at MIT from the education point of view, and then I'll also show a bunch of research projects that are currently ongoing and some of the things that I have been working on as well. I arrived at MIT here to teach around 2016, 10 years ago. As you can see, before then we only had maybe one or two classes, and as I got started, we introduced more and more classes. And the demand for this is huge. There are so many people here who love music and who love technology and find these courses really fascinating. And this has happened because I've developed some classes, but also then we started hiring more people. So we have a lecturer in music technology, and more recently we've hired some new professors in music technology as well. We also have a new music building, which we're really excited about. So if you've ever been to MIT, you might know about Kresge Auditorium, and there was a parking lot next to Kresge Auditorium, and now instead of a parking lot, we have this, which is a new music building. We're really excited about it. It's got 3 different structures, kind of under one sort of combined roof, maybe. One is the concert hall, which you can see here. It is a concert hall in the round. There are 4 audience sections seating all around the musicians who are in the middle of the concert hall. That's this building over here. This is the world music rehearsal room. So here you can see the Balinese gamelan instruments. We also have Senegalese drumming instruments. So that's this space over here. And then this building here is offices and also research areas. So for example, we have a makerspace, and that is a place that is exclusively a makerspace for music. So you can see we have the 3D printer and the laser cutter, and there's some speakers here on the sides. Everything here is about making musical gadgets. This is the lobby connecting all three buildings. And my office is right here. I'm going to wave to you now so maybe you can see me from right there. Okay, we are excited about this building, and this is where a lot of the new master's program is taking place. This program is a joint effort between a few different areas of MIT, which is both exciting but also hard to do. It is generally, as you might know from academic institutions, everyone kind of likes to do things their own way, and so combining things can be sometimes hard, but there was a lot of great energy behind trying to do this. So so music and theater arts, that's my department, the School of Engineering, and MIT has a College of Computing. And these three organizations together essentially helped create this program. It is a one-year master's program, and it has two different tracks. So for kind of two different types of people. One is one is a research track, where you actually write a full comprehensive master's thesis under advisement from one of our professors. And the other we're calling the practice track. It is the Masters of Applied Science. So there's no thesis, but it's an intensive set of courses that you take over 1 year to really boost your potential. The nice thing of this is that we think we'll have a lot of different kinds of students coming in from these two different areas with different goals. So we're excited about the diversity of students that are going to come into MIT for this. Just a little bit, the thesis track is really set up only for MIT undergraduates. So if you are currently at MIT and finishing your senior year, you can apply to this program, and we will, and this is where you'll be writing a thesis. The reason this is only for MIT students is really most master's degrees are 2 years, and in order for this to work in 1 year, you really need a little bit of a head start. So you really start your senior year where you take one graduate class and you start planning your thesis. And then when you are in your graduate program, you take a few remaining classes, but mostly work on your thesis. We have a funding model where we fund all students 1 semester. And typically students in this track might find a TA-ship or something like that. At the end, we think they're ready to go on to industry or to PhD programs in music technology. The next one is the Masters of Applied Science. And this program is really open to anyone. You have to have a strong engineering background with good music, or maybe exceptional music background with good engineering. So, kind of maybe you're not amazing at both, but that's okay. For the first semester, we sort of get you up to speed so you are fabulous both in music and engineering. And then in the second semester, you can take more advanced classes that really combine music and computation together. Also, 1 semester of fellowship funding for this program, and we think it's a real career booster for people who, might have inclinations towards this area, but might not have had the experience, and we think this will really give them that so that they can get high quality jobs in industry. Or maybe if they're really interested in research, maybe they transfer to the SM degree. So in some cases, I can imagine someone coming in for this program and deciding they actually do like research, and they move into the thesis program as well. So that's the plan at least. The timeline we have in place looks kind of like this. We're growing it slowly over time. So just in September, October, we just started. We admitted only the SM program, so only the thesis track. We admitted 5 students, all 5 students accepted. They will start this fall. And then for the following year, we will open the application for both. So starting in the fall, anyone who wants to can apply for the applied science degree. And then in the following year, we will have 5 of each students. And then we're hoping that the year after that, we ramp up to 20 students. for both degrees. And that's kind of the steady state, about hoping to graduate approximately 20 students per year. Part of this whole program was that the deans who helped us put this together realized that we can't just have a program without faculty. And so the result is that there are 3 new faculty hires as part of creating this program. So I've already been here for 10 years. Ian Hatwick has been here for about 5 years. But we have 3 new faculty hires. One is Anna Huang, who comes to us from Google Magenta. She was the author of the Music Transformer paper, one of the kind of seminal papers that is is the kind of foundation for a lot of the AI generative music that we see today. Mark Rao, who comes to us from a postdoc at McGill and Stanford, it works on instruments, instrument acoustics, measuring instruments, and audio effects, and that area, and signal processing. And then we have one more that we are very close to announcing. We can't quite announce it yet, but we're really excited about this. This is a senior hire, so someone who's going to come in as a full professor. So between that, we now have the staff to really be able to run this program. And let me show you some example research projects that are currently currently happening here. So one is the MIT Laptop Ensemble, and this is something you might have encountered. We have one here at MIT. These kind of started from a tradition of laptop orchestras. I think the first one might have been in Princeton, and then they sort of moved, at least in the United States, across to different parts of the country. This is a kind of maybe a smaller ensemble, and Ian Hatwick leads it. You can see here there are students who are connecting their laptops to keyboards, and sometimes you can connect laptops to gestural controllers where you're moving your hands, or it's tracking, or maybe a camera-based system. As well, here you can see live coding, and if you're not familiar with this is essentially you are typing a code into a computer that is interpreting it in real time and automatically generating music as a result of that. So there's a lot of different configurations, and the particular interest we have here in terms of, from a research point of view, is looking to see what kind of music can you create in a network situation, right, where you have a number of people who are connected to their instruments, their devices, but those devices are connected to each other, and what kind of collaborations can you have, and what kind of performance practice can you set up in this kind of situation. Another example, completely different, is something that we worked on this past summer. So Mariano was a student of mine over the summer with Patty Tang, who is an ethnomusicologist. Patty leads the Senegalese drumming ensemble at MIT, Rumbach. They have a wonderful performance program here. One of the things that we have been doing is putting some of these courses online. So MITx is an online set of courses. It's part of edX, which is similar to Coursera, if you're familiar with that. And the idea here is, okay, well, you have a course online about world music, specifically about Senegalese rhythms. And how does this course normally go? If you take an online course, maybe you have some multiple choice questions, you see some videos, you read some stuff. But really, what we want is something that is more about the music itself, right? And how can we get people in an online course to engage more musically? And so what we did was we created a custom module that plugs into this online course, and it actually demands of you to play the rhythms that you learn from a master musician, and then you have to reproduce those rhythms, and only if you do well in that, then can you advance or can you pass the course. For those of you who have played some of the music games like Guitar Hero, this might look a little bit familiar, so I'll just play this so you can see what it's like. So you can see here what happens is the person has to press either the F key or the J key at the right time as the notes fall down. You can see here in the corner, it tells you how you did. Did you score well or not, and of course you have to score well enough in order to kind of pass this online course. Another example of a collaboration that is happening here at MIT also is between Mi-Yoon Kim, who is our piano faculty, and Pranith Namburi, who is at the MIT Nano Lab. Specifically, he does measurements of human motion. And Mi-Yoon, being a pianist, is very aware of one of the things that happens a lot with pianists playing at a very high level, and that is injuries, right? There's a lot of times where pianists will play, they practice, up to 8 hours a day. If their technique is even a little bit non-optimal, it can lead to injury. And so what happens with this project is that here they are in the lab. We're using a Yamaha disc clavier, so we measure everything that the pianist is doing, performing on the piano, including how all the keys are moving, how the pedals are moving, the sound that's coming out, obviously. But at the same time, we're also measuring the pianist. As you might be able to see here, Mi-Yoon is wearing a little device on her wrist. This is an ultrasound device. So you might look at this and it might look familiar. If you've had a baby and you go in and you do an ultrasound, you can see the little baby in there. Okay, so this is not a baby. These are wrists. This is and what you can see here is the bones, the radix and ulna, which are the two main bones in your wrist. As Mi-Yoon is playing, we measure the distance between these two bones, and you can, based on that, you can gain a lot of insight about how the person is moving as they're playing the piano, what kind of motions they're doing, and are those motions helpful to the music and also helpful to prevent injuries, or are they problematic? And this is very early research, so it's not like we have too many findings so far, but one of the things we are noticing is that if the motions are correlated to the rhythmic activity of the music, that seems to be a good thing. So as you can see here in red, this was a playing through a technique that did not, that there was a lot of strain in the arms. Whereas here is a set of fingerings that Mi-Yoon was using that was better, and you can't hear the music here, but you can see that these signals actually look more rhythmically, and they are more rhythmically aligned with the music that she was playing. So we're excited to see where this goes. Probably in the next year or two, we'll have more results from this. Anna Huang, who came to us from Google, you might have seen this. This was a few, maybe 5 or 6 years ago, but the Bach Doodle, which was the first kind of large-scale online generative music algorithm. And this was a system trained on all the available Bach chorales, so 4-part harmony chorales. And what happened was users would enter some kind of musical line, like say the soprano line, and then the system, I think it was using something like a diffusion type network to generate the remaining three musical lines. 55 million users created 55 million melodies in only 2 days when this came out. And something more recent that Anna's working on with her student Nitya is looking at, this is in the audio domain for vocal synthesis, specifically in Hindustani music, where there is often a call and response kind of situation. Perhaps in a performance, the one instrumentalist or one musician will create some kind of melody line, and then there's a response to that. Maybe sometimes in a student-teacher situation, the same thing can occur. So I will play to you what this sounds like. So this is the prompt. This is a human singing the initial part. Okay, so that's what that sounds like. Here I will play for you that original part, and also the AI model as it is generating the pitch contour, which is the response to this particular prompt. Okay, so we're kind of excited by where this is going, and we're looking at different models for how human and the AI might interact with each other as they're playing music that is very specific. Unfortunately, there has not been a huge amount of research on music that is not kind of Western classical music, but this is one of those efforts which is pretty exciting. Another example of some research happening here is with our professor Mark Rao. He is studying instrument acoustics. So you can see here he's measuring with an impact hammer the acoustic vibrations of the guitar, and then being able to say something about why a guitar sounds a certain way, and why a luthier might decide to make a guitar one way or the other way, depending on what acoustic goals they have for the instrument. But also we're studying ancient instruments. So here at the Museum of Fine Arts in Boston, they have one of the largest historical instrument collections in North America. I think something like 1,500 artifacts, including, like, look at this thing. This is a violin shoe. I don't know what this is. Some kind of wind instrument, and maybe an ocarina or something like that. At any rate, they are working with the Museum of Fine Arts and a collaboration between Mark and someone from material science, Ben 17, material science at MIT, to basically try to figure out what these instruments sounded like and what it would be like to play them. A lot of these instruments cannot be played today because they are too fragile. For example, there's one instrument that is a flute or a pipe. It's 2,500 years old. You're barely allowed to touch it. You can't play it. If you did, it would probably fall apart. So they're using CT scanning and understanding the materials and the acoustical properties of the instrument to try to understand what it sounded like and also understand what it was like to play it back then. And I thought I would also then just go through some of the projects that I've been working on recently. I've been working a lot with mobile phones. I kind of find that sort of interesting. We all have technology in our pockets. And of course, these are very sophisticated computational devices. There's a lot you can do with them. So that's kind of what I've been trying to do. So here's the first one. This is called Concert Queue. And Concert Queue is an application that I've been working on for a little while now for a mobile device. And here's the premise. So you come in and you want to see an orchestra, a classical music orchestra, and say you're not necessarily a musician or you maybe didn't have classical training, and so a lot of times people find this intimidating. You're trying to find out what's going on. You look at the program book. For example, this is the Boston Symphony Orchestra program book. Oh my God, it has 128 pages. Is anyone really going to look at that? Maybe, probably not. If you do look at it and wonder what was playing today or what is about to be playing tonight, you might find that Claude Debussy Nocturnes is on the program, Nocturnes, which is wonderful. But if you want to find out about the music, there's one sentence here buried deep inside that actually says something about the music itself. Fanfare is heard softly in the distance, okay? So I think this is the wrong approach. This is not what you want in terms of understanding what's happening musically, okay? What you actually want, I think, is something like this. Something where, as soon as the music is happening, someone can whisper in your ear or tell you something about what is going on in the music at that moment in time, in real time, as the music is playing. Like, for example, like this. Or this. Or maybe later on. And then finally, and so the way we do this is that, you go to a concert and everyone says, please turn off your phones. And so I kind of like being contrary. And so I think, well, what happens if you go to a concert and we tell you to turn your phones on or keep them open? And what we can do is this. And so this is an example of Concert Queue in action. On your phone, you see there's this red line that moves across the bottom, and that is the timeline of the current piece you're listening to. And as you get to a tick mark, a new message appears, a sudden break, a parade starts in the distance, strumming harps, muted trumpets. Or maybe we can have images. So what was the inspiration for Debussy as he was writing this piece? Maybe it was this painting. Or maybe we can have some simple notation. So even if you can't read music, you might be able to kind of follow along the contour of what is happening with the wind winds instruments like this. The point of all this is that this does happen on your phone, but we don't want you to stare at your phone all the time. So in other words, the message appears really quickly. Maybe it lasts on your phone for maybe 5 or 10 seconds, and then it fades to black. And so the idea is now you're listening to the concert. But you have a little bit of a sense of what you should be listening to. And of course, the way this works is that this timeline, while it is set up in advance, so all these notes have to be notated ahead of time, the synchronization happens in real time. And so no matter how fast or slow the conductor is playing, or if they have a fermato or a bigger retard or whatever it is, this follows the music exactly as the music is happening. You can see here, we had another version of this with the Boston Symphony Orchestra, actually for the same piece. This is the conductor, Andres Nelson's. They had these screens in the back, so you can see conductor cam. We also put concert cue on the TV set. So it can work either on your phone or it can go to large displays. Some people, of course, find this controversial. Should you have screens in the concert hall? Maybe, maybe not. But maybe one day, maybe sometime soon, this can all happen with augmented reality, where you have your own personal experience of seeing augmented information and you're not bothering your neighbors. So this is a program that we're constantly developing. And there's more and more orchestras here using it. We have surveys, of course, so one thing we're interested in is, does this help? It looks like it does. We don't want it to be too distracting, so it seems like most people do not think it's too distracting. Some people might find it a little distracting. That's something we can work on to improve. Do we show the right amount of information? Maybe a little bit too much here. But the encouraging thing is that it seems like the vast majority of the people do want to try it again if they found the experience useful. I felt like I was interacting with the music, made me appreciate Haydn's genius as I followed what he was trying to achieve. I gained a deeper understanding and context of the music, right? So that's what we're trying to do, trying to get people to have a deeper experience with music, no matter where they are, get them one step closer or one step deeper in their musical journey. So that was that, and then I'll present one more project that I worked on, and then maybe after that we can open it up for questions. So this is a project from back from COVID. So as probably happened all across the world, everything had to shut down when MIT had commencement, which is the celebration for the graduate students. We realized that this could not happen, and the whole event had to be virtual. And so, which is really sad, right? This is what MIT commencement looks like normally. It's this wonderful event with thousands of people outside, and all that had to go away. And so instead, we were trying to create an experience for our students to have them somehow feel together, even though they're all apart, using the power of music. We wanted a system where everyone could feel like they were part of something bigger, and so everyone could contribute something. How do you have every single person, or as many people as possible, contribute musically, even if they might not have any musical talent, they might not be playing an instrument, they might not know how to sing? That was the interesting dilemma here. And so our solution was that we are going to get every person, as many people as we can, to sing exactly one note. Okay? Now, I think everyone can hopefully sing a note, even if it's out of tune, maybe we can fix that later, right? We will have a pre-written piece of music, maybe something to do with MIT. We're going to try to get as many voices as possible, maybe 1,000 voices. And maybe we do some kind of video animation to go on top of that. So that was the basic idea. This was one of my first virtual projects. Here I am. You see I need a haircut. This was a virtual team. Most of these people had never met before, but we all started working together. This was the music that was written by my friend and colleague and composer Evan It's based on this MIT song, All Rise Ye of MIT. The tempo starts at 30 BPM, goes up to 272 BPM in the middle, and then back down again. So it's kind of this nice arc of a piece. It only lasts about 3 minutes. I had to prototype this, right? So the idea is, can we have different people, every one of them just singing one note, and then can I stitch that together and create something that sounds okay? What will it sound like? So, of course, this is my family. We're all stuck at home together. And so I asked my family to just sing one note. And this is me. Okay, so then I put these together, and this is what it sounded like. Okay, so like not bad, right? Like maybe this has some hope. So after this prototype, we were kind of convinced that maybe this is something we should go ahead and go forward with. This is what the music looked like. So the piano roll notation, you can see it starts. What you were just listening to in the prototype is just these first few notes as it gets crazy and fast, and then slows down towards the end. This is all data, right? It's all MIDI. So as the piece was completed, we had statistics about the piece. It had 850 total notes, 48 unique pitches that span a pretty wide range from D2, pretty low, but male basses can sing that all the way to quite high. Over here are D6 and the D6, and this is about the distribution of notes. And so we were thinking, okay, well, what if we get, here we have, this pitch over here. And could we get a whole bunch of people to sing all these different notes, and then we combine them all together? To do that, we had to collect notes. So we created a custom website that runs on your phone or your computer. And it basically tried to give you a little menu of things you could try. Okay, so first you would enter your vocal part, soprano, alto, tenor, bass. The difficulty, meaning are you an expert singer or not a very good singer? And then we would play an example pitch. So you would kind of pick one of these that you would try out. It would give you the instruction, sing ah for 2 seconds, or sing ta for 1 second, or something like that, right? For the length, the note that we needed and the length of the note that we needed. And then you just recorded yourself with a video, 10-second recording, and that's it. And then you submit it. This used the MIT security system, so we knew exactly who was submitting the note as well. Okay, this is the timeline of notes coming in. Okay, each one of these is how many notes were submitted per day. So over here, this is kind of the prototype period before we announced it. This is when we announced the project. We got a big wave of interest, and it died off. This is when we did another marketing blast to get people to submit more notes. That's kind of how it happened. We did in our beta test, which is over here, this part here, we got some examples of people singing. I was like, okay, well, they're singing a note, but what can you see about these people that maybe looks a little sad, right? They don't look happy here. We had them sing oh and ah. Okay, so when someone's singing ah or oh, this is what they look like. And we thought, well, we want this to be kind of a happier thing. How do we do that? So someone had the idea, what if they sing a different syllable? What if they sing T? So we changed that, and we said to everybody, sing T, and then you can see that just makes people naturally look like they're smiling. I find this fascinating because we have an inventory of notes, right? So as you pick a note that you want to sing, then it's almost like shopping, like these are the notes that are available, these are what you're supposed to do. But the notes that people submitted were not necessarily what we asked them to sing. Right here, for example, someone sang this note way more times than we needed. whereas sometimes we needed more notes than we had. This was interesting. Sometimes people sang the right note, but the wrong octave. Sometimes people sang a note that was a fifth off. Sometimes people sang something completely different, like not related to what we asked for. But this is the notes we got. Well, you work with what you get. So we have this audio sample pipeline. We have the video of a 10-second video. We extract the audio from the video, normalize, find the boundaries for the note, so we have an exact match of when the note starts and ends. These are all done automatically. Noise reduction, pitch estimation, then pitch correction to make the note kind of sound in tune. Sound restoration, using some EQ, noise removal, and then finally placing the note at the right moment in time in a DAW that we were using. So we're using Reaper to automatically place all the notes correctly. So this was all done as much as possible automatically. Some of this had to be done by hand, but most of it was automatic. I'll give you a sense of what this sounds like. So as the pieces put together, here's what it would sound like if we had a little section of the notes where everyone is singing not corrected, not pitch corrected. Oops. Now this is what happens after we correct the pitches and tune everything up. Very much better. And then we also added a light instrumental background just to kind of give the piece a little more structure. It was also really fun to see how people contributed. Some people did wacky things, even though we asked for one voice, people sometimes had their whole family or did crazy graphic effects, friends trying to sing together, Pokemon, of course. So it was really nice to see that even though we're all kind of isolated, what people did to be creative. We ended the whole video with a photo mosaic. So this is all of the people who contributed notes. Plus other alumni. This is the famous MIT building that you're used to seeing from screenshots, so everyone understands this as being the iconic MIT building. This was also using some gigantic optimization algorithm to figure out how to place the pictures in the right place to create the MIT building. I thought I would give you a little bit of a sense of what this sounds like, and hopefully this works through the video. So I'll start this here. And I'll skip this part because that's just me talking. And then just to go a little bit further ahead, that's my presentation. And happy to take any questions about it.
Okay, there, one moment, I'll come to you.
Hello. My question is regarding you mentioned the master's program, but you have like a PhD program?
A PhD program. So currently we do not have a PhD program in music, okay? But all of the professors that I mentioned have a dual appointment between music and engineering. And as a result, they have PhD students, but the PhD students have to apply through the School of Engineering. So they typically have to be computer science or something like that, maybe mechanical engineering. They apply to MIT through the PhD program through engineering. Then they say they want to work on music technology with the professors that I showed you. And so in fact, we do have PhD students in working on music technology with our professors, but their degree is going to be an electrical engineering, an EECS type degree, an engineering degree, not a music technology degree, which of course is somewhat similar, right? But that's how we're doing it right now. So the answer is kind of yes and no. There are PhD students, but what we are hoping for, and this might take some time, maybe 5 years from now, is to actually introduce a PhD program in music technology that we can offer from the music department, and then we can have it more customized to what we want. For example, maybe we don't need quite as many engineering-focused classes or computer science-focused classes on the qualification side. Maybe we can have people who are more hybrid, maybe they have an artistic practice too. So that's where we're hoping it goes in the future.
Great, thank you very much.
Any more questions? Okay, I think we're going to move on to the next speaker. Shai, you want to present the next one coming up? And Eran, if you can stick around and join us for the panel, you're more than welcome to do so. We'd love to have you.
Yeah, sounds great.
So we are opening the third session, 21st Century Musicality, and we're happy that we have with us Shlomo Dubnov. To start, Professor Shlomo Dubnov is Director of the Center for Research and Entertainment and Learning at the UC San Diego's Research Center, Collegiate Time, and teaches in music and interdisciplinary computing in arts program. His formal education combines music and computer science, graduate from the Jerusalem Music Academy in composition, holds a doctorate in computer science from the Hebrew University, and prior to joining UC San Diego, he served as a researcher in IRCA. His presentation title is Music, Co-Creativity and Improvisation with Generative AI.
Thank you so much. It's a pleasure being here. Thank you for organizing the conference, and it almost feels like home. I was also teaching here once. I guess some people here attended a talk I gave on Tuesday, where I was talking about the improvisation technology and projects that I've been running at least for the last 20 years in collaboration mostly with IRCA. And so for this presentation, I'm going actually to talk about more recent work that we have been doing in CSD. And very briefly, this is the music building and the Contemporaries Music Center, where we have this wonderful concert hall that is on the cover of my pretty recent book on deep and shallow machine learning for music. And we have a joint lab with third lab. I'll introduce Taylor Kirkpatrick, mention him later. My center, Krell. So we all aggregated together with some other faculty and many students. This is the Music AI group. So this is the computer science building, and this is the Qualcomm Institute, where my center, Krell, is centered. So I've been working on music from the perspective of statistical machine learning, some statistical signal processing, but I've been also doing stuff more broadly about style and statistical modeling of text and other media. So here's a reference to the book Structure of Style with Shlomo, who I think got his PhD here. At least I think Moshe Koppel was his PhD advisor. And so I've been working on cross-cultural media communications with various people, and also this book deals with text and style, authorship, architecture. And in the last 3 years, I've been part of the European Research Council project called REACH, and some of the research I'm going to show is actually performed under that umbrella, and this is done in collaboration with Eran in Central Pompidou. This is a forthcoming book, Lecture Notes in Deep Learning, which doesn't talk so much about music, but we try to include there some of the recent stuff, like diffusion models, which have not yet been kind of showing up in a lot of literature. So, just showing the broad spectrum, I think, in terms of cross-cultural communications, and we mentioned how what we do and metaphor, culture are related. So, as I said, it's not only music. We have a symposium in AI for cross-cultural understanding and tolerance. So, if somebody wants to host something like this in Israel, I'll be happy to do that. Where you can see how much AI could influence, like agents, speech to text, and of course, questions of fairness benchmarks, because really AI and communication are super important. So going back to more musical stuff, this is the project I mentioned, the European project on co-creativity in cyber-human musicianship with my long-term colleague Shai and also Mark Chemillet and myself. So I kind of talked about this on Tuesday. This is kind of the OMAX improvisation paradigm, where we started with generalizing Markov models using L'impulsive, and first open music L'impulsive application. François Pachet took this further as a continuator. Then we switched to OMAX, and a lot of these models that are still being state-of-the-art today in terms of people going on stage and recording corpus and improvising on that corpus. But this is what I call shallow learning, and the reason I can mention this, first of all, because this is a big part of what I've been doing. And another one is that I think it's kind of a good introduction also to say or see how today's deep learning technologies work. But even in this PyOracle version, which actually I don't think I showed that slide on Tuesday, you can see that actually what we have a recording, we have a corpus. On the left, it's an audio, and we do, using whatever the algorithms are, construct some kind of an indexing structure on top of that recording, which allows us to remix it. Now, you can see in the middle that there are multiple features, MFCC-centered amplitudes, zero crossing speech, chroma. So, depending on the feature you extract, or depending on the representation, you actually find a different structure here. So, what we have is kind of a vector database, if you wish, that allows us to query the actual audio with different inputs, and this is the query threshold that you see here. So I think this kind of model of interacting with the corpus in some sense carries forward also to deep learning models. And of course we have representation learning that is now automated. So instead of having multiple features, we have multiple heads. instead of this factor oracle, the pi oracle structure based on the factor oracle algorithm. We have attention models, and of course I'm not claiming that we were the first ones to create attention. This is a very different system, but I think that the overall principle is that you have data, you need to extract features. These features can be then queried and can be learned in terms of their temporal overall kind of predictability. And then you can use that to retrieve instances or pay attention to other instances in the corpus that you have in order to predict the next node or the next frame. So the focus of this presentation is really deep learning and generative AI. Of course, this is a collaborative process. As I said, it's our Mosaic group in the CSD. So I'll talk a little bit about the recent work since, I would say, 2003, 4, in which one aspect is really the audio representation. The HDSAT, the hierarchical token semantic audio representation. So this kind of a little bit of technical talk, but I'll jump to some musical examples as I can cover these things. So having a good representation, we actually were able to construct CLAP, which is the language and audio pairing or contrastive models. So in image processing, CLIP, I think some people might have heard about this. A CLAP is the equivalent, and actually these works got us quite a lot of attention. Now using CLAP, now we have a text and music embedded in the same space, and that allows us also to control diffusion models. So we came up with this music latent diffusion model, which is the equivalent of stable diffusion in images. So the musical DM. Other work that we have produced recently is the using language models, the music transformer. So one was mentioned, the music transformer. Let's say that's a minor work that took language models and applied them to symbolic music. And so we did a follow-up work on multi-track transformer, and now we're also doing multi-track diffusion models. Another work that I don't think I'll have time to show today, but singing voice cloning and timbre transfer, and then some results where we kind of trying to think about information dynamics, which is a theory that I was kind of developing over the years to use this also in multi-track settings. So a lot of the work that we're trying to do is actually map instead of just modeling music, which is, of course, a very important aspect of any generative model. We also now try to think how one music can relate either to another music, so multi-track, or how it can relate to text, or how it can relate to images. So in that kind of cross-media, multimedia aspect, I think a lot of the deep learning now allows really exciting stuff to happen. So this is the list, kind of the collaborators, the students and colleagues related to this paper. Kechen, music student, Tornike, also a music student. Karen, who did the voice, is a mathematics student. Ganesh, he's a CSE student. Herman, he's now faculty, but he was a CSE student. And of course, Julian Taylor, faculty in electrical engineering. And this is kind of a partial list. So why representation learning is so important? Well, in NLP, everybody knows about GPT. Here's the BERT and the original T5, the encoder-decoder representations, and they actually created a revolution in how we model text, how we understand language. In computer vision, ResNet, EfficientNet, or Visual Transformer, I mean, these are tools where neural networks actually used without, I would say, a specific goal. Maybe they're trained on a specific goal, but then what we are interested in is applying this network to our data and actually having some kind of a vector, some kind of an embedding that represents the data in a smart way. So what happens in audio? Well, if we have a good audio representation, you can do a lot of stuff with it. You can do source separation, you can do music generation, classification. So I will not talk about our source separation application, but this is also one of the works that Ikea, who's now a researcher in Adobe, created. We have basically a zero-shot source separation algorithm where you give it a short example of a sound without having the data trained on that specific sound, and it actually is able to generalize and separate that specific sound. So, so this is our kind of music representation work. It was trained on sound event detection task, where we use something which is actually based on visual transformer, where we take a spectrogram and then we kind of raster scan it, creating some sequence of tokens. They're passed into this kind of hierarchical transformer, which is this visual transformer kind of inspired architecture. And everything is trained using tokens, which are sound event detection and training data. But the good thing is, or the interesting thing is that once it's trained, we have a representation that's very powerful. Now, why this is interesting? Because then we can use this for, as I mentioned, CLAP, so the large scale, contrastive language audio pre-training. And this is published in ICAST in 2023, although the paper was published the year before on arXiv. And as you can see, it got quite a lot of citations in the last 3 years. And so what is CLAP and why is it important? So as I said, if we want to have some kind of relation between audio and text, we can actually collect data. So what we have here, this is the way CLAP is trained. We have analysis of audio and we have analysis of text. Here we use pre-trained text encoders. Here we can use our own HDSCT. Of course, in that specific paper, we compare this to other PAN, a pre-trained audio neural network, and other versions of text. But the whole idea is that you try to create this correspondence mapping between text and audio in our case. And the whole thing is that you eventually want to have the pairs of text and audio which make sense together, because this was in the training data. We collect a lot of captions and labeled audio data. So the correct caption that corresponds to the audio, you want it to be on the diagonal, which means this is the true corresponding pairs. But if you have the wrong pairing, you want that embedding, that representation of audio and text to be very far away. And this is what this matrix shows. Now, why is this important? Well, I'm just kind of to give an idea of what it is. Usually it was done just kind of to improve so-called contrastive learning, self-supervised model when you have a lot of data. And what you want to do is, if you have, you actually start with an anchor, and you find a positive example, and you want that positive example to be close to the original one, and then you find a negative example, and you want to pull them apart. So, of course, you can do this on triplets, you can do this on multiple negative examples, and this is what Clip did, and we did this with audio, which is the CLAP. Now, I think the important question, and kind of, I think, responds to some of the discussions we had in the morning, is this contrastive learning when it's applied to different types of media? Because here we have two images, but actually what we had is one was image, one was text. Okay, so just kind of not to confuse how that relates to the previous ones, you can have an anchor, which is an audio, and a positive example, which is a text that matches that audio, and negative text that doesn't match the audio, and vice versa. You can have your anchor as a text and have two different audio examples, one matching, one not matching. And then eventually you end up with having some kind of a vector space, some representation where things which are related are positioned close to each other, even though they came from very different media types. So what I think emerged from starting using this, and I'll show this in some musical examples, is people think about contrastive learning as semantic space. But if you do this in very distant spaces, actually, is this really semantics? Does it reflect meaning? Or maybe this is metaphorical mapping. Okay, how this creates conceptual blending between unrelated media types that then you can kind of use to express yourself in one type of media and will automatically find a matching sequence in another one. So in Musicality, we took the latent diffusion model, and here CLAP, we have this audio CLAP and text CLAP. meaning that you can provide a text, it will create a vector. You can provide an audio, it will create a vector, and depending on what is the task, you can actually try to now recreate or use the diffusion that I'll maybe mention in a second what it is. But the way it works is that we start generating from some noise an image, and either the text or another audio example could be used as a guidance. What you see here, it basically kind of nudges during this process of creating that image or that sound, in our case it's sound, on the latent space, because there's a VA encoding. This is why it's Musicality, and L stands for latent. While it generates, kind of imagines a sound emerging from noise, the text little nudges it at every denoising step, so it actually will find a sound that matches that description. So it gives us really text to audio possibility. This is an example of diffusion in visual domain. You start with image, you add noise, then you try to denoise it. And if you have these models, then eventually you have multiple steps that allow you kind of start generating images. And then once you kind of combine it with text, now you can actually tell the generator what you want it to be. So we have the musical DM, as I mentioned before, the same graph, but here kind of emphasizes different applications. If anybody would like the copy of the slides, you can have try all of this out. Everything is available, but it actually allows 3 different ways of creating music with these technologies. One is text to music, as I mentioned. You can have music to music. You can also have style transfer, where our engine is actually the diffusion model. Now, the recent paper, actually just presented in ICAS last month, was generalizing this to multi-track music separation and generation. So if before, what we have seen was like a single sound that is generated either stochastically or randomly, or generated guided by text. Now, this work actually generalizes this to 4 tracks. That's why it's called multi-track. It's true, it's always trained on that specific set of tracks. You have, guitar, drums, and piano and bass. And so, unfortunately, it's not a very general model. But what it allows us to do is really now do the same trick, but on different tracks. So we can add, we can actually create various situations. You can provide one track, it will create, and it will actually complement this with all other tracks. You can create accompaniment, you can generate either everything from scratch, or you can generate one track given the other 3, and all the possible permutations. So I won't run through the demo page, but again, these slides will be available, I hope, so whoever, or just contact me. You can see the different examples of actually what happens. You can compare the original tracks, and you can remove a track, it will generate a different track for you. It's kind of interesting to see. Usually, actually, the AI is a little bit more excited. It provides much more active music than what human would do for some reason. And so, a little bit about how you could use this creatively and where the metaphor comes in. So, one thing is you can take a poetic text, like this poem of Rilke, and with this poem you actually can use ChatGPT to translate this to musical prompts, and then plug it into Musicality. So this is not an example I will show, but this is a concert we had last year in Musées in France with, actually we collaborated with sound poet Jaap Lonk with his sound poetry, and we generated materials based on his poem, and then plugged this into SOMAX, and it was kind of combined improvisation with generated materials done actually by automatically using Musicality from the text that he gave. So maybe I'll just play a short excerpt from that performance. Maybe I didn't share audio. I mean, if there's no audio, it's going to be difficult. Should I share it again, or?
I think you should set the audio output GH.
Oh, on my, it's on my part. So no, there's this audio. Oh no, it was just my sound was broken. That's just okay. Okay, thank you. I'll leave this as a teaser because of the time limitations. So, forward with that. So the idea is really, these are the poems, that's how they were written, with these kind of cryptic symbols, verse 1, verse 2. For each one of them, ChatGPT was able to do this metaphorical mapping really from that to an audio prompt, mysterious and ethereal piece. This was plugged into Musicality, and everything was then created as a bank of sounds that we plugged into SaMoT, and then we had the live interpretation. Last piece that I'll mention is, and I will not play it because of the time limits, but we actually won an award on, and it was in this December Big Data Conference, but there was also a competition. We actually used the same idea to interpret a graphics course by Cornelius Cardio. I don't know if you're familiar with this, but I mean, that's a seminal work of 173 pages of these kind of paintings, drawings. I myself also participated in some performances of this with humans, not related to AI, and it actually takes quite a lot of creative thinking. How do you make music out of this? So what we did is actually pretty much the same process, but this time we used the GPT-4 image understanding option, and from that we actually asked it to describe an interpretation. We also added some prefixes ourselves. Do you want to generate this as sine waves, a string orchestra? It's experimental. And there is the additional autoregressive aspect where you basically feed the previous 15 seconds into the latent diffusion models, so it actually tries to complement the next 15 seconds so we can actually generate. So we, from the 30 pages, we didn't do the 173. For the 30 pages, we generated 11, 12 minutes of music, and so everything was kind of automated. So I think these are kind of the ideas. Okay. So I think I will just summarize what are the design principles for co-creative interaction. And I think in that sense, you need a generative model that can learn probability of musical messages, because communication is kind of messages, the sequences of tokens from musical data. And then you basically random sample it, kind of a very disappointing view of creativity. But then you add some query to make it interactive. You influence the output, and you also want it to be responsive, understanding some context. You can add prompts, you can add a RAG type of stuff, and we also have done some work on that. Then you can start mixing types of media. So the cross model can respond to text, can respond to images, and it gives us very surprising understanding of what images are, what music is. Call it semantic, call it metaphorical. I don't know. Now you can think about this as an agent. So I think this aspect of agentic communication becomes more and more prominent, and the question of this emerging communication between you or the score or another musical track or a text to a generative model, I think this is a very exciting field of research. So then all kinds of questions of pragmatic communications, rational speech act, and things that people were exploring, of course, metaphor as I mentioned, and specifically, talking about music understanding. We continue this work on so-called music information dynamics, trying to extend this to multiple tracks. So we have this multi-track extensions via transfer entropy, which is a type of work that has been also really popular in terms of estimating musical surprisal. I think early in the morning Dubnov mentioned surprisal or somebody else, but these are kind of ideas that we have been researching. So sorry for taking extra time, and thank you.
Thank you very much, Shlomo. We will send the questions in the end, so please welcome Hadas, a composer, sound artist, educator, activist, teach composition, electroacoustic, and music at the Bar-Ilan University. At the Tel Aviv University, sorry.
Okay, so hello. Today I'm going to talk about a topic that interfaces with some of the things that were discussed earlier today, such as Marco's discussion of constructing meaning from a work of art, Lior's work on instrument construction, and some of the items we saw outside during the lunch break. So I'm glad that there are a lot of topics around it, and that allows me to talk a bit less and refer you to other people. I'm going to start by saying something very non-academic, which is that I find sound production to be something that's very magical, in the sense that if we don't know what it is, it's very non-intuitive. And I'm a violinist, and I've played the violin for many very small children, 2, 3 years old, and they're always in complete awe when they hear a sound coming out of a violin. There's nothing in their experience or intuition that would lead them to believe that moving a bow like this or anything on a string would produce this kind of sound. And with this sort of magical perception begins a process of meaning making, in which they, through experience, they develop expectations. And then this idea of drawing a bow on a string and hearing sound is no longer magical or surprising, because we learn over time that this is what happens and this is how instruments work. And other abstractions that we can relate to that, people playing other kinds of instruments, that blowing through a pipe will make a kind of sound. All these become a concept that we're very familiar with. And then this becomes something that is ingrained in our understanding of the world we see around us. It's a meaning that's been created, constructed through experience. Now, if I look just at this example of a child hearing an instrument for the first time, I'll backtrack. I'll say that one of the things that I'm trying to do in my work is to find this magical moment again. How can we take our expectations and and the meanings we've already made, and find a place where they're not entirely constructed, and where we can sort of slip in and create some kind of new surprise in the musical world, or in the sound world rather. And going back to this example with the child, if I take that example apart, I have a physical acoustical aspect, which, like Leo mentioned earlier, we have the 3 types of levels of sound production in an instrument. We have a gesture. The gesture puts a string or a pillar of air column into vibration, and then the body of the instrument resonates it. So there's a very clear acoustic and physical process that's going on here. And on the other side, we have a cultural and philosophical phenomenon, which is someone observing these things and making a concept out of it that has some validity in the cultural world around us. So these are two kind of separate ideas, and just as I'm trying to find this moment, this magical moment again, I'm also trying to find a point where these two ideas can interact with each other, and how can we use technology to deconstruct what we understand about these two topics, the physical acoustic and the philosophical cultural. I use these terms as a reduction, of course. It's much more complex, anthropological and psychological and so on and so forth. I don't pretend to understand all these fields, but on the level of musical culture and physical acoustics, there's a point where I want to use technology to create a new relationship between them that we're not used to. So that's one intersection. And before I go on further, I'm going to show a few examples because otherwise I'll just talk a lot to explain something that could be seen. So I'm going to show an example of an installation made by one of my students in Tel Aviv a few years ago. And maybe I'll just start by playing it and then I'll explain what's going on. תשקיעי קצת? ותפריד קולות? So this was in the lobby of the Music Academy in Tel Aviv. This is the student explaining to other people how to use the installation. So what we're seeing there, and there's of course all the talking around, so I'm sorry if it's not very clear, but very acoustic lobby at lunchtime. So what we actually see here a bit earlier, I'll show, is that we have broken instruments. These are just the bodies of some of the instruments. Most of them don't even have strings. They're old, broken instruments that are not in use, obviously. And what the student did was he took tactile transducers, exciters. You saw them in action outside on the pianoid model. And he attached them to the instruments. And then he took a Beethoven string quartet. He recorded each instrument, and then he played each instrument's part through that specific instrument, through the body of that specific instrument, which has the tactile transducer attached to it. So the transducer plays the part, and it comes and it resonates outside of the actual body of the instrument. Now, it's very clear that nobody is playing the instrument, so if we think again about our physical cause and effect chain, that somebody needs to make a gesture, and then something needs to go into vibration, and then there needs to be a resonance, we don't have that first part. There's no person making a gesture. So this already breaks our expectation of how an instrument should be working. The second part is that the instrument is clearly broken, so even the second part of this chain, the vibration part of it, can't happen because there are no strings. And the only part we have left is the third part, the resonator or radiator, as they all called it, which allows the whatever is being played electronically to obtain the qualities of an actual acoustic instrument. And those qualities are both a very clear physical presence, localization. If we heard, just as I said the first time a child hears a violin, it's surprising, it's magical. I can imagine that the first time that someone who only heard live music on acoustic instruments hears a loudspeaker, hears a violin playing on a loudspeaker, that would be equally magical because the violinist should be present, the violin should be there. We're not seeing any of the sources, but we're hearing it. Again, this is something that we've all experienced so many times that it's completely normal to us. It's not something special. But the loudspeakers also have a very specific quality that tries to realistically convey the original instrument, but also has a very virtual quality. Usually they're spread in a hall in a way that doesn't necessarily make the sound very localizable. It's much more diffuse, especially if we have a stereo system up front where it doesn't have the presence of an actual musical instrument, even if the musical instrument is being represented very accurately through the loudspeaker. But when you have the actual body, resonating body of the instrument there, then it's very localizable, it's very clear where the sound is coming from. It's very clear that there's a physical aspect of it, there's the quality, which is the spectrum being produced by the resonator. So we have the presence and the quality, but we don't have the quality which we would associate with a live instrument that has a human agent operating it. But we don't have the human agent operating it. So we're sort of doing a mix and match between these different types of music production that we know. We're taking the virtual aspect of a loudspeaker, but the very concrete aspect of an actual live instrument, and eliminating the human agent. And the human agent is obviously there, but not pushing a button, not actually playing the instrument. And then this creates this new kind of situation where we have all these stimuli that we recognize, but we don't recognize them put together in this way, and we don't recognize them, these certain causes, as being the causes of what we hear as the effect. So, one moment. זה יתנתק? I'll show one more video of this. Just the university took it for an event called the Scientist Night. So there were children walking around and trying to play with us, and that created a sort of similar experience. Oops, sorry. This was an example that was made for a wide audience to come and enjoy it. And I want to talk about how we can integrate this both into such installations, but also into concert music. And not just the idea of transducer-based technology, but also any kind of technology. I'm going to focus on transducers, but the idea is using any kind of technology that doesn't have to necessarily be very complex or very advanced to take what we already know as our concert listening experience, and rather than adding more layers on it or creating technology that augments it, we're going to try to look inside, see what connections, subconscious connections we've already made, try to break them and reconnect them in a different way. And it can be done in many different ways. I'm going to give a few specific examples. Okay, so we saw this. A brief explanation of how this works. So on the left here we have a loudspeaker. The way a loudspeaker works, it has a driver, or also something that would be like an exciter or a transducer. Basically metal plates in a coil that move up and down and vibrate. And then on a loudspeaker we have a diaphragm and a cone, which make the sound radiate outwards from that. And the diaphragm and the cone are supposed to, if they're well constructed, they're supposed to represent all the frequencies available in a way that that's similar to how our ear hears frequencies, and then the sound is very realistic. What the exciter does is it's really pretty much only this part of the loudspeaker, the part that's moving, but it doesn't have the membrane or the cone, so there's no resonance. There's no resonance that comes with it. But once we mount it on a surface, that surface becomes the resonator. So if I put it here, the podium, and I play music through it, the podium will play music. If I put it on this box, which will probably sound quite nice, then this will produce the music. The actual exciters, they come in all sizes and type and strengths, but this is roughly the size of the ones that I tend to use for musical instruments, 40 watts, 4 ohms of resistance. That doesn't get very loud, but it's usually safe to use with actual instruments. It doesn't overcharge the instrument and overheat it or anything like that. So the idea we saw in the string quartet was attaching these to the instruments and playing, and then the instrument serves as this mounted surface. I'm showing some images of different pieces and installations that I made, so you can see how different types of transducers are attached to instruments. Here you can see one on a cowbell, here on a wind gong. This is a different type of transducer that doesn't actually touch the gong, but it's attached with a metal bracket, so the vibrations are passed through the metal. And this is an example on another broken violin and another piece. 2 violins which are hanging, and they each have a transducer attached to them, and sound is coming out of them. And exciters, sorry, transducers can go both ways. Exciters are specifically to turn the electric signal into vibrations. So I want to recap the ideas I presented here before I present my own work. So we have the concrete kind of sound quality and presence, which we get when we have a performer who we see live, so not via television or a screen. Someone who we're seeing live playing a musical instrument. We have our cause and effect chain. We have the concrete presence of the player, the localizable sound. Then we have on the other end of that the virtual aspect, which would be something like a hi-fi loudspeaker, which can recreate for us the sense of an actual musician or orchestra, or for example, an electric keyboard playing samples, which is, again, it's an actual keyboard, it's a musical instrument, but there's no acoustic relationship between how the instrument is being used to what we're hearing. We're hearing something completely virtual. If we're hearing the samples of a French horn, then the French horn isn't there, and the keyboard isn't trying to imitate the French horn, it's just serving as something to push buttons. So these are, the virtual aspect is something that I think since music technology has existed, has been a focus of much of the work. And today obviously is going much further with augmented reality and with 360-degree sound. Basically the virtual is being constructed, a lot of the research is going into how to make the virtual more realistic and more accessible. And that's a very interesting field. And what I'm looking for is this hybrid position, which would be something like the acoustic instrument with an exciter attached, and no human agent, but again, it could be made in other ways. It could be, for example, using a musical instrument as using the acoustic qualities of a musical instrument as a sampler. For example, taking the body of a violin and tapping on the body and having and actually capturing the resonant qualities inside the body and using the different resonances to trigger different samples, for example. So there's some kind of mixing of using the actual acoustic qualities and the physical presence and the spectral qualities of the instrument and the virtual aspects of the technology. So just a summary of what are we trying to do. We're trying to deconstruct our understanding of the cause and effect relationships in sound production and then to reconstruct them in ways that are counterintuitive. Again, to create this magical, surprising, expectation-breaking effect. And we want to deconstruct the relationships we've learned between the physical and acoustic and the philosophical and cultural. And this doesn't necessarily need to be something that's done only through technology. We can sometimes do this by observing other cultures and just seeing that the way they understand things are completely different, and then using that to create a new kind of dialectic. And we want to create a hybrid space that makes use of technology while maintaining the concrete presence and qualities of musical instruments or resonant objects. And the bottom line of all this, why do I want to do all this? I want to use it so I have new expressive possibilities, new discursive possibilities, new dialectical possibilities when composing a piece of music or creating an installation or any kind of multidisciplinary project.
Yes.
Mm-hmm. Yeah. Okay, so now I'll just show a few examples. So this is a piece called The Secret Lives of Electromagnetic Transducers. It was released on LE Records. This is an image of the ensemble playing it. And in this piece, there's a scheme that makes it so that each instrument plays, the sound of each instrument is treated electronically, and then it resonates through another instrument. So here's an explanation of what is being resonated where. And this is a schematic of it, so quite complex. And I want to give just a few audio examples of how this can sound. So first example is of the trumpet player who is being amplified on a woofer, which is just the driver of a loudspeaker, just the lower frequencies, and it's still fairly localizable. And there are two other players who are wearing these woofers around their necks. It's attached to a strap. The guitarist and the pianist. Each one of them is wearing a woofer on their body. And during the performance, they also at some point walk around, so the sound is also moving. And the trumpet sound is being is treated electronically and is being produced through these two other speakers. So I'm going to give a small example of this, and you can hear how the space changes because of the presence of these speakers. Maybe? So the sound is moving very quickly between the two loudspeakers. Another example is of the flute, which is going into two such transducers, which are lying on piano strings. So they are making these kind of sounds, but also using the soundboard of the entire piano to create a larger resonance. So this is an example of the flautist playing and her sound returning, being played delayed through the piano. And in a later section of the piece, the flautist, all that the flautist has already played is accumulated in a delay and played inside the piano without her doing anything. And she can start and stop this multi-delay by playing a note loudly enough, so we can hear the resonance of the piano very clearly. It's difficult to, without seeing visually and being there, it's difficult to understand it simultaneously, but when they're, so I gave examples with delay, but when they're playing simultaneously, then there is this very eerie sense of a flute sound and a piano resonance at the same time. One last example, the bass player had a transducer inside the bass, so this also allowed for feedbacking while playing, but also, one of the moments was a conversation with the bass.
Istalek.
So this is the bass player and the player telling each other to go away. And very last thing is that this can also create an element of a personality or character in the instrument, which many composers use for musical theater with objects. So that's another aspect of it. Thank you for listening.
Thank you very much. Next is Gili, musician, educator, and founder of MIA Music Inspiration Academia Israel, a center for training music teachers, developing innovation tools for music education. She is building a community of music teachers focusing on the integration of technology in music education.
Hi everybody, good evening. I'm on the low tech ticket for myself. If you had asked me a few years ago where I thought my daughters would learn about the world, I would have said music for sure, maybe books, school, I'm not so sure. Definitely not TikTok or Instagram. I remember one evening we were sitting at the dinner table. I looked at my daughters, each one of them glued to a screen. I'm sure you know this situation. And scrolling video after video after video, 1 second here, 1 second there. They were physically present, but mentally somewhere else. And as a mother, I felt something rise inside me, like frustration and kind of helplessness. This wasting time, I thought, this is a distraction. This isn't real learning. They're becoming passive, completely passive, so like expecting life just happen to them. As if instant growth and knowledge will somehow arrive from the next video. I believed in something else, completely else. I believe in deep learning, in making mistakes and coming back to try again, in the power of repetition, of building something with depth. I believe in creating anchors, habits, values, and quiet rituals that helps us hold our ground in a world that constantly pushes us to rush, react to move on. But it's not, as we all know, it's not just my daughters, it's all of our students. This is the world they grow up in, a world that scrolls fast, reacts instantly, and moves on quickly. The digital age has reshaped how they think, how they learn, how they interact, and as music educators, we can't afford to keep teaching through old lenses. If we want them to stay with music, to truly commit, to grow through it, we can't just teach the note, we have to redesign the way we teach. Students today are not less capable, they are differently wired. Their nervous system are shaped a digital world, one that offers constant stimulation, rapid rewards, and endless streams of context. It's not a broken system, it's just a very different one. Oops. This environment has taught them to shift focus quickly, to expect immediate feedback, and to process multiple inputs at once. These are not bad skills, in fact, they can be incredibly powerful in the right context. But learning music, entering the world of music, asks for something entirely different. It's based on a different set of skills that increasingly rare. Present, patient, repetition, deep listening, and ability to stay with something even when it's not so easy. And here lies the tension. How do we teach something so fundamentally deep in a world that moves fast, reloads quickly, and doesn't wait? It's not a battle between old and new, it's a call for translation. Our mission is to build a bridge, to take what we know about growth, mastery, and meaning, and make it accessible in the language our students actually speak. When I first faced this gap between how students learn and what music demands, my instinct was to resist, to hold on to the old ways. I wanted them to adapt to me. But when I entered the world of design thinking and innovation, and something clicked. I realized if we want people to persist, don't just tell them to try harder, design systems that support persistence. The solution is not to fight the digital world, is to borrow from it, to learn how to motivate, how to structure progress, how it captures attention, and to bring those principles into our teaching without compromising depth. In my work with teachers, music schools, and students, I focus on 3 key strategies. The first one is to break learning into smaller, achievable steps. Every small win creates momentum, and that momentum builds consistency. It's like leveling up in a game, every application, but with scales and etudes. The second one, we help students see their progress, not just their mistakes. Tools like trackers, reflection chart, and color-coded goals make the invisible visible. They help students understand where they are in the process, what learning actually looks like, and how they've already come. I love working with tools that invite reflection and reveal the different layers, learning from fundamental skills to final outcomes. And the third one, we don't say you need to practice more. We say let's design a routine that works for your brain, your schedule, and your way of learning. We move from blame to co-creation, from telling to teaming. Because building sustainable habits isn't about a willpower or motivation alone, it's about creating systems that removes friction and makes success feel possible. These changes may seem small, but they shift everything, and they build a bridge between the world our students live in and the world we want them to invite them into. Let me give you a quick example. A student of mine, talented, sensitive, full of potential, kept losing motivation between lessons. He practiced less and less, he avoided difficult pieces, and when I asked him why, he simply said, I don't know, I just forget, or I don't feel like it. I guess it sounds familiar. Instead of pushing more content, we focused on building a system, and we started with small, simple steps, a daily 3-minute goal, a colorful tracker, and a short reflection question like, what felt easy, what was challenging, what do you want to try tomorrow? Within weeks, everything changed. He practiced more, yes, but more importantly, he began to feel like the process was his. He wasn't just following instruction, he had ownership. He anchored the habit of being in daily contact with his instrument and with music. And once that habit was in place, the next step came naturally. He practiced more deeper, longer, and more meaningful. And most of all, he started to enjoy it. Playing became part of his life. This isn't just about one student, it's about how we redesign the system that supports real learning, real growth, and real persistence. That's why a big part of my work is dedicated to helping people build strong, sustainable foundation, helping students develop daily practice habits, not by waiting for motivation, but by building structure, identity, and a sense of ownership, helping music teachers create working routines that support both artistic growth and financial stability, and helping business owners, many of them creatives, design daily systems that move their work forward just like practicing an instrument. Because at the end of the day, it's all about the same muscle, the discipline of showing up with intention day after day in service of something meaningful. That's why, along my work with teachers, entrepreneurs, and mentor, I'm building something bigger, a community of performing musicians, educators, community leaders, and creative entrepreneurs. Together, we're creating a new kind of space, it's called Hamsha, one that bridges tradition and innovation together, and one that fosters peer learning, experimentation, and real collaboration. A space where musicians are not just interpreters of music, but creators of change. We are not just teaching better, we are redesigning what it means to belong, to lead, and to grow in today's musical world. The challenge we face isn't about fighting technology or giving up tradition, it's about combining the two. Designing music education that meets this generation where it is without lowering the bar and without losing the soul. Because in the end, it's not about faster or slower, it's about meaning, presence, curiosity, and the willingness to stay in the process. Thank you very much. This is for the low-tech like me.
Thank you very much, and I'm happy to invite Revital Hollander to be our last speaker for today. Revital founded the Tel Aviv Music Technology Community activities where she had organized more than 40 meetups, where she had workshops, international music, art, tech, hackathons, and activities connecting local and international music tech community, bringing the gap between artists, scientists, and more.
Hi everyone, I'm very happy to be here. I want to congratulate Yuval Adler, Goni Perez, Professor, for the first time I say Professor Shai Cohen, and the Department of Music for having this conference. And I'm from Adelson School of Entrepreneurship at Reichman University. I was until this year the head of the computer science and entrepreneurship program. And I was asked to talk today about the ecosystem, maybe not the ecosystem, but the community and the activity that we have here in the music technology scene, let's say, not ecosystem, but scene, and a little bit about my work and how it is connected to everything that is happening here. Okay. So basically music is everywhere, and the role, we ask ourselves what is the role of music technology in our lives, and maybe how we can contribute to our lives using music technology. And this is, I think, the main topic of this conference, talking about this thing, music technology, and how it combines art, science, and tech. Okay? So interdisciplinarity is the challenge, and it is an interdisciplinary, let's say, field that combines between technology, engineers, computer scientists, sound designers, musicians, and sometimes people from other disciplines like psychology, cognition, and other fields. And it is a challenge whether we think broad or deep, and how we collaborate with people from different disciplines in order to develop something that is meaningful, whether it's a new initiative or a research project. And okay, so this is the first challenge, and the second challenge is to see what we have here in Israel, in this scene. For many years, it was like a little bit of something here, like a company or a department or a small department or a course or something that is happening here. And I was asking myself for many years, why don't we have like a real center for music and technology in Israel? So I founded the activity for music and technology community, as Shai mentioned. It is not really active in the past few years, but there are many things that are happening, I think, that are continuing this activity. I want to tell you a little bit about what is happening here. Many thousands of people, I think that much more than 3,500 people that are doing something with music technology in Israel. We found out that we have more than 192 music initiatives, let's say initiatives, and some of them are really real companies and startups. And there was a lot of activity in this field, showing that people are really interested but something is not supporting it. Maybe not the academy, maybe not the industry and other, let's say, players in this field, okay? So I will not talk about the hackathons, but if you're interested in what happened in the past few years, I think that these two examples of two hackathons that happened in the past few years, and many others that were organized by other people, show that even the international community is interested in what is happening here. The Austrian embassy and other research collaborators from worldwide. Okay, so how can this community or activity or this thing that we're doing here and other activities can contribute to the ecosystem? I think that first of all, it's the education. You have to educate people to let them know the material and to be familiar with the field. Research, I will talk about it a little bit, and entrepreneurship, of course, because this is what will bring us more and more activity and money. So education is something interesting because I found out that music tech as an interdisciplinary field is a very good tool for education and creativity. I did like a lot of workshops and courses in many institutions, including Reichman University, where we developed prototypes. We learned some music, some computer science, some a little bit about music interaction and interactive tools, and built many projects where students had to ideate, explore, and work and develop in a maker lab. They were not learning regular, as a regular students by listening to teachers, doing lectures and assignments, but more like teachers were mentors. They had meetings and they developed innovative projects. What is really interesting in this field is that people come from many disciplines. They share their skills, not in the specific discipline they learn, but also in others, in other skills that they have, and they're doing a little bit of software, a little bit of design, hardware, and UX, UI, and it is all combined to one project. So, as an educational tool, students become more familiar with this material, but also bring something else or learn to work in teams and develop something that is related to music, to something they love, and they bring what they want to the table. So these are a few examples of projects that were designed. Some of them are creative tools or instruments. Some of them are more like experience tools like a musical escape room. Some of them are tools for people with disabilities. I will just, and musical games that were developed by taking regular games, traditional games that we play, and regularly we use our visual ability in order to solve or to play the games, and we converted them to games with sound and music. So you have to develop your ability to hear something and to memorize sound, for example, using a musical memory game, or solving or walking in a labyrinth using a sound that will guide you, etc. Okay, so it's like many things that people that are just studying computer science or music or something else can develop together because they are, they have all the skills and the knowledge they bring to the table. Also, entrepreneurial projects like musical apps that can develop to new initiatives. It's also part of the education, demo days, that is part of the finalization and the demonstration of the project. So this is a small example of something that students developed in. Why don't we have the video? Okay, maybe it will take time. Of an electronic pantom, like handpan. It's a different name for the same thing. But the students were both computer science, electrical engineering students, and design students that designed this pantom. It is an electronic pantom. They developed it in like 3 months, including learning to use the software, working with sensors, and designing and working with the laser cuts, etc. And I'm not sure you can hear the sound, but you can see the experience. Maybe how can I share the sound?
You need to
On
change
my
the
computer, share sound.
you need to change the audio output.
The audio output, okay. Okay, so I will just say that, okay, one second. Maybe when I share it, I share the sound. Oh, it's on the So the thing here was, first of all, to overcome a few challenges. First, to design an instrument that is electronic and tries to be like an acoustic instrument in a way. It is more like a controller. It's not an instrument, but still the feel, of playing on this instrument and tapping on it was the target. Was our goal? Okay, yeah. And then, okay, never mind. And then we had a few challenges of avoiding collisions and all the technical stuff when you design something like this, like hexagon with hexagonic pyramid, I don't know how to say, and try to make it work and the design. And here, maybe in this photo, you can see the amazing work. I think that the two the design students that thought about, our light and sound and how it can develop and change during playing. Okay. And then another project that also.
You want to try to copy the URL to the browser and see if it works there?
I'm not sure because it's on the. Okay, all right. So in this example, you see an instrument that you play in space. Okay. Now it's an instrument that basically we built, and it's like. You have a few items in the space, and those items are context-based, which means that they are aimed for a specific domain or, let's say, scale or musical context. And even if you are not familiar with music and music playing, you can play it and achieve something really meaningful. And we reduce complexity and let people enjoy playing and something meaningful for them. It's on my drive. No, it's okay. Okay, never mind. I will just show it. Okay. Yeah. If you want, I will send you the video. So what we have here is like an instrument that you can play in the air. Okay, and you can feel how it is to do all kind of gestures. without touching anything. Hopefully, one day AI will be able to create for each player, even a non-musician, the instrument that is best for him in terms of physical characters, like where to put each element, and his level in music, etc., etc. Okay. So I will. Okay. Entrepreneurship. I just want to say a few words about the ecosystem and the startup ecosystem in Israel. It is still developing. Many startups rise every year, and we had a few success without big success, but still. We did a research on the music ecosystem and tried to map it. I'm sorry that it's only until 2020 or 2021, I think. But we see how it is growing in a way. In the COVID, it was a little bit, down. Many startups deal with music creation and consumption, and many startups in Israel deal with education and digital health. You can see how streaming, business, and the audio and hardware. This is what we found. Fundraising. You can see that it is not consistent. There are some times that are better, sometimes it's worse, but all in all I can tell you is that for startups in Israel, it is still difficult to raise funds in Israel. It is much easier outside, of course, where there are no music hubs, and I'm still hoping for it to be better. So maybe we have good news. We have Universal Music Group in Israel, in Tel Aviv. They are trying to promote startups, and they are connected to Abbey Road Studios Accelerator. We have another accelerator, a new accelerator, Music Tech Innovation Lab, or MIC, that is also based in Tel Aviv. They are organizing a conference on May 26th. I work with them quite a lot. I think it's a good initiative and a good hope for, promoting and accelerating the startups. And you're welcome to participate in this conference. It's more industry-based, of course. You can see the startups that are working there today and maybe get some inspiration. And that's it. If you have any question about everything,
אתם יכולים לשאול שאלות את כל האנשים שהיו הדוברים בסשן הזה? מי שרוצה, בבקשה.
נגיד שזה במקום הפאנל, כי כולנו כבר אחרי יום ארוך.
הזמן רץ לנו.
כן.
שאלה קטנה טכנית, מה ששמענו בסוף מהדיבור הזה, תסתלק, זה הבאס מדבר?
זה אלגנט. נראה לי אפשר לשמוע מתי כאילו שני איכויות אקוסטיות שונות, אחד מהם זה היה הנגן והשני זה היה הבאס.
הבאס שמדבר,
כן. אז נגן בסוף הבאס, מדבר אליו זה מילים של טקסט משיר, ולאט לאט הטקסט ממשיך לעבור דרך הבאס והנגן.
הטרנסדיר של בתוך הבאס שמהדהד את מה ש...
כן, בדיוק.
טוב, אנחנו נצא להפסקה קצרה ונסיים את היום הזה עם קונצרט של איגוד הקומפוזיטורים.
לפני ההפסקה דברי סגירה קצרים של גוני ושלי, ואז מחכה לנו בחוץ יין וגבינות, אז נעשה את זה ממש קצר. בזמן שגוני מגיע לעלות context switch. Hi everyone. Closing remarks, and then we'll go outside for wine and cheese. While Goni is loading the slides for the closing remarks. First of all, thank you for coming. thank you for staying until now. Please stay for the concert. At the very least, have some wine and cheese when we get out of the hall in just a minute. What we'd like to talk about a little bit now, I'm going to break the flow that we have in the slides, but if you, as we mentioned in the beginning, and maybe you've noticed throughout the day, Goni and I, and with the help of some others, some of them here, have started a nonprofit that is, basically our goal is to build a continuation of this, a music tech community with some kind of longevity so that we can have these exchanges more often and for longer. Yeah, we might not have the slides and we might not need them. That's really the bottom line. If you go outside to the posters, there's QR codes for the website for the conference. If you just delete everything after the .org, that's our website for the nonprofit, and you can scroll all the way down and join our mailing list, and that's how we're going to keep in touch, basically. That's really the gist of it. Anything to add?
I think we can discuss our vision and all the things we prepared in the slides.
Over wine and cheese.
Yeah, I think that's actually a good idea because there's still a concert ahead of us. So I see that not a lot of people stayed. Hopefully we have an influx of people coming in for the concert. But if you're here, please stay for the concert. Okay, and enjoy the wine and cheese. Thank you.